right, guys. So we're going to pick up yesterday, or excuse me, on Friday, we introduced the periodic trend of electronegativity and talked about how that relates to polarity. We are going to start in and look at the other periodic trends that we need to be aware of. First one that we're going to look at is atomic radius or size. This is very similar to radius of a circle that you have done in math class. But in an atom, there is not a nice defined outer edge of that electron cloud. So how they define atomic radius is it's 1/2 the distance between the nuclei of two atoms of the same element when they're joined. So roughly halfway between the nuclei is going to be where the edge of that atom is. But like I said, it does not have a nice defined edge. The actual trend you need to be aware of is atomic size is going to increase from top to bottom. So it's going to get bigger as you go down a group. And then it's going to decrease from left to right across a period. So the biggest elements or biggest atoms are going to be in the bottom left-hand corner of the periodic table. Smallest ones are going to be in the top right-hand corner of the periodic table. And kind of why this increases and decreases. Going down a group, the number of energy levels increases. So you're going from, like if we were in the first column, you're going from putting electrons in 1s to 2s to 3s. As we go down to each new row, we're adding a new energy level. The electrons in that outermost energy level are further away from the nucleus, and they're shielded by electrons closer to the nucleus from the pool of the protons. So I'm trying to think of a good way to explain this. If someone were in the front of the classroom and they threw a tennis ball, the people that are most protected from being hit by the tennis ball are the people that sit at the back, because they have everyone in front of them kind of blocking or shielding them from that tennis ball being thrown at the front of the room. Same kind of thing occurs. Whenever they have electrons in those inner energy levels, they're blocking the pull of the nucleus from those outer electrons. So since those outer electrons are blocked from the pull of the nucleus, they can spread out and the size of that outermost energy level increases. Whereas going across a group, the number of energy levels doesn't change. So if we look at like the second row, we would add electrons in that 2s energy level and then into p. Those are the same energy levels. So they're the same distance away from the nucleus. So there's no increase in shielding. There's no additional inner levels of electrons to block the pull of the nucleus. But going across, the atomic number increases. The number of protons increases, which is going to be able to pull on that layer of electrons more, kind of causing it to shrink in towards the nucleus, which is going to cause the size to decrease going across a period. With radius, we also have to look at the radius of ions. So remember, ions are charged particles that are produced when an atom gains or loses electrons. So our cations are positively charged ions. These have lost electrons to become more positively charged. These are typically going to be our metals. And what happens is, since an electron is lost, there are more protons than electrons. So the protons are able to pull on the electrons more tightly, pulling them closer to the nucleus, making the ion smaller than its original atom. Whereas an anion are negatively charged ions. They gain electrons to have that negative charge. These are typically going to be our nonmetals. And since electrons are gained, there are more electrons than protons. The protons cannot hold onto the electrons as tightly, which in turn makes the ion larger than its original atom. A way to remember these is I kind of use the analogy of weight. So think of if you lose weight, you get smaller. Cations lose electrons and get smaller. If you gain weight, you get bigger. Anions gain electrons and get bigger. So that's one way that you can kind of remember the trend with those. We also are going to look at ionization energy. This is the energy required to remove an electron from an atom. So for it to completely lose that electron and it be transferred to another atom. We're going to typically deal with the first ionization energy, which is the energy needed to remove one electron. Even if it's something that is going to lose more than one electron, it only loses one at a time. So the trend for that first ionization energy is that it decreases from top to bottom within a group. So it gets smaller going down, and it increases from left to right across a period. This is the same trend from electronegativity that we did on Friday. So the largest ionization energy is going to be in that top right-hand corner of the periodic table. The smallest is going to be the bottom left-hand corner. If it is something that loses more than one electron, there is a value for the second ionization energy. So the energy needed to remove that second electron. There's also a third ionization energy if it has to lose a third electron. And generally, as more electrons are being removed, it requires more energy. So if it's something that is going to lose 3 electrons, the second ionization energy takes more energy to remove that second electron than the first one did. That third ionization energy is going to take more energy than the second or the first. So as they remove more electrons, it gets harder and harder to remove them, requiring more energy. So the actual trend for ionization energy, and I'm going to try to move this down a little bit, that way we can still have our trend there. So going down a group, we said that ionization energy decreases. The atoms are larger going down a group, making those electrons further away from the nucleus. And since those outer electrons are shielded from the nucleus, it's easier to remove those electrons. So the outermost electrons, when they're further away, are easier to pick off. So this is why the energy needed to remove an electron decreases down a group. So you could think if we're in a horror movie, kind of the rule is you never like go anywhere by yourselves. If we're in a big group and there's a serial killer, the people that are easiest to pick off are the ones on the very outside of the group. Whereas the ones kind of in the center of the group are going to be harder to pick off. And then kind of going across a period, we said that atoms decrease in size going across the period. So remember, there was no shielding because we're in the same energy level. However, going across from left to right, there are more protons that were pulling harder on the electrons in that energy level. So since it's smaller and those electrons are closer to the nucleus, it is harder to remove those electrons. So that's why the energy needed to remove electrons increases going across the period. And like I said, this trend was the same as the trend for electronegativity. However, remember, electronegativity did not include noble gases. Ionization energy includes noble gases. So that's kind of a difference between the two. Right. So there is a way to remember the trends, and we call this the roboto dance. So you're using your arms to kind of make these wedge shapes. So I'm going to draw it in that top right hand corner. I already have the right arm drawn. And let me switch colors and I'll draw the left arm representation. So the overall trend is with your left arm straight up and down. If you look from the width of your pinky down to the width of your elbow, your arm increases in size going down. So that represents that going down a group, ionic and atomic radii increases. So your left arm is representing the radius trend. And then you're going to turn it horizontal across your chest. And notice from left to right, it goes from your elbow to the tip of your pinky, which is decreasing in size from left to right. So where your elbow is that largest radius. And then your right arm is all the other trends. This one, you're going to kind of replace your left arm. So it's going to start going across your chest, horizontal, and from left to right, it goes from your pinky to your elbow. So it increases in size going across. And then you're going to drop it down where your fingertips are pointing towards the floor. And you have your elbow on top going down to your pinky. So it decreases in size going down. So the largest ionization energy and electronegativity is that top right corner. This is just kind of a way to help you remember the trends if you're not so good at memorizing those initially. All right, and we're going to switch gears and we are going to look at intermolecular forces. These are forces between two different molecules that we're going to see. So molecules can attract one another in a variety of ways. Now, these intermolecular forces or intermolecular attractions are weaker than actual bonds. So these are weaker than ionic or covalent bonds. These a lot of times determine the state of matter that we're in. So it'll determine if a molecular compound is a gas, liquid, or solid at a given temperature. And it all depends on the strength of those forces. And there are 3 different forces that we have to be aware of. 2 of them are considered van der Waals forces. And then the third one are hydrogen bonds. So we're going to look at these individually. So our van der Waals forces, these are split up into 2 different forces. We have our dipole interactions and dispersion forces. These are the 2 weakest attractions that there are. These were developed by a Dutch chemist, Johannes van der Waals. And the dipole interactions, remember we talked about with differences in electronegativity, we end up with that polar molecule that has the positive end and the negative end of a dipole. So dipole interactions are where polar molecules are attracted to one another. So the positive end of one molecule is going to be attracted to the negative end of another molecule. So these occur between oppositely charged poles. So if we have something like HF, fluorine has a lot of electrons. It's the most electronegative, so that end is going to be slightly negative, whereas the hydrogen end is going to be slightly positive. How it interacts with the hydrogen fluoride next to it is that positive and negative end are going to be attracted to one another. So that dotted line is our dipole interaction. Just where those 2 oppositely charged poles are attracted to one another. Now, the dispersion forces or London dispersion forces, these we are going to see in everything, but this is typically what we're going to look at in nonpolar molecules. And this force is caused by the motion of electrons because electrons are constantly moving. And what happens is they will unequally distribute at some point in time while they're moving around, which causes this dispersion force. So what happens is when one atom's electrons move, it can influence the electrons of other atoms around it to move in the same direction. And this is due to electrons being attracted to the nucleus of another atom. So I'm going to try to draw this. This one, like I said, is the trickiest one to kind of wrap your head around. So here I'm going to use the nucleus as an X. So here we have two kind of nicely balanced nuclei where all the electrons are evenly distributed in that electron cloud. Well, what happens is one of those, the electrons are moving around and they all decide to kind of cluster on that right side. What that does is the atom next to it, all of its electrons that were nice and evenly distributed, they don't want to be close to the electrons of that other atom. So they will all migrate away from those electrons that are there. Now, this will then redistribute because the electrons are constantly moving around, and it will go back to normal. So this is just where the electrons, since they're randomly moving around at any given point in time, they're not evenly distributed for a split second, which causes a dispersion force between these two molecules, where it's kind of repelling the electrons from one atom and making the electrons in the other atom move around. But like I said, this is going to be a split second, and then it's going to go back to normal. So this is something that is constantly changing. A way to think about this is kind of in our school building. We generally know, if it is 7 o'clock in the morning, if every student in the building is considered an electron, most of our electrons are going to be kind of near the commons and cafeteria area, or even out in the parking lot at that point in time. Well, 7:15 bell rings, everyone should be in classes. So there's going to be students on every single hallway in the building. Well, then class time or class change occurs. There's still electrons in every room of the building. Whenever it's third period, though, we have a lunch. We might have a whole hallway that's empty, and then a cluster of people in the cafeteria. So the electrons or the individuals in the building are not evenly distributed anymore. But once a lunch is over, those people go back to their classroom, and then another group of people go to lunch. Then we have a different empty hallway. So this is something that is going to be constantly changing throughout the day or throughout time. All right, and our next force that we look at are hydrogen bonds. And the name of these is kind of misleading because this is still an attractive force. It is not an actual bond like an ionic or covalent bond would be. So a hydrogen bond is an attractive force in which a hydrogen is covalently bonded to a very electronegatively charged atom. Also, weakly bonds are attracted to an unshared pair of electrons on another electronegative atom. And this, you're going to see those very electronegatively charged atoms. To remember which ones work, I say hydrogen is fun, F-O-N. So hydrogen bonds are going to occur whenever hydrogen is attached to either a fluorine, an oxygen, or a nitrogen. And that's because there's such a large difference in electronegativities that it causes this strong attraction. This is what happens in water. So I'll actually draw water so you can see what this looks like. But you actually saw this in biology, whenever you were looking at like DNA. What holds the DNA bases together are hydrogen bonds, and also with like proteins being folded is due to those hydrogen bonds. And hydrogen bonds are the strongest of these intermolecular forces. So remember we said these are weaker than actual ionic or covalent bonds, but hydrogen bonding is stronger than dipole or London dispersion. So what this looks like is when we have water, excuse me, my pen turned off. When we have water, now a hydrogen bond is still just a very strong dipole. So we have kind of a negative end of water and a positive end of water. Well, here we have that hydrogen oxygen bond that forms. So what happens is the water that is next door, that hydrogen is going to be attracted to that unshared pair of electrons on the oxygen. So this attraction is our hydrogen bond. So it's just that hydrogen, because it's positively charged because all the electrons kind of migrated towards the oxygen, is attracted to those electrons on the oxygen next door. All right, and to do just a quick recap of those intermolecular forces, I remember we said the intermolecular forces are weaker than actual bonds. So ionic and covalent bonds are stronger than any of these three forces. We said hydrogen bonding is stronger than dipole forces, which is going to be stronger than dispersion forces. Dispersion forces are the weakest of all of them. And it's because they are so short-lived. Like we said, it's going to unequally distribute electrons for a split second and then go back to normal. So this slight attraction comes from electrons not being evenly distributed around the nucleus, and then it goes back to normal. Those dipole forces we said are stronger than dispersion forces because they're constant. If something is polar, it is always polar. So it's always going to have an attraction to other polar molecules. So this attraction is from the slight difference in electronegativity, making part of the molecule slightly positive and the other part slightly negative. So remember, a positive and negative end from two different molecules can attract one another and interact. And then hydrogen bonding is the strongest of the three. This is also constant because it is, like I said, a strong dipole. It's due to a larger difference in electronegativity between the hydrogen and its oxygen, nitrogen, or fluorine it is attached to. This comes from them being so far apart on the periodic table and by the heightened attraction due to small size of atoms. You're not really going to have to identify these in molecules at this level. That's more of what happens at the AP level. But you should know which one is stronger than the other. And you should be able to identify them based off of their definition only.